Here we see that an electron is flowing from the right position to the left position upon the influence of an electric field, which is going from the right to the left. So basically the direction of the electric field is given from positive direction to the negative direction. So basically you have higher electric charges here and lower electric charges on the right hand side, which gives you an electric field on the right hand side as shown here. Now an electron is moving under the influence of this electric field. Now remember that for a positive charge, if there is a positive charge, it flows along the direction of the electric field, right? So it has to flow from the higher potential. So this is the higher potential electric field, which has the positive electric field directions to the lower potential. So for a positive charge, if it moves along the electric field, the potential reduces because it's going from higher potential to lower potential. And also the potential energy reduces. For a negative charge, since the negative charge is moving from lower potential to higher potential, opposite to the direction of the electric field, so therefore the electric potential of the electron or negative charges would increase. But since you see the electron will be repelled from this negative direction, right? If there is an electron, it will be repelled from this negative direction and it will be moving towards the positive pole. So therefore, the potential energy would reduce. So basically, for an electron in this case, moving from right to left, for an electric field direction given here, the electric potential would increase and the potential energy of the electron would decrease. Therefore, option D is the correct option. And here we see two positive charge sheets in the x-axis and the y-axis direction, and they are uniformly positively charged. And we have to find out the equipotential surfaces with respect to the positive x-axis in the first quadrant. All right. So now we know that the electric field equations for a sheet of charge is sigma by 2 epsilon naught. So that's like for one direction. So for example, if I'm considering the y-axis sheet of charge, so basically the electric field will be going in both directions, right? So in each direction it will be sigma by 2 epsilon naught, right? For both the left and the right hand direction. Now you see my electric field, because of the y-axis sheet, is on the right hand direction, right? The electric field. Now the electric field, because of the x-axis, it also has the same magnitude, since it's a sheet of charge with in each direction, upward and downward, to be sigma by 2 epsilon naught. Now my electric field, because of the x-axis sheet, is in the upward direction, and because of the y-axis sheet is in the right hand direction. Therefore net, I will have, basically if I see a net electric field, and these are, you see, not dependent on distance, that means it has a fixed electric field. So therefore for the y-axis electric field, I will have on the right hand direction. For the x-axis, I will have in the upward direction. Therefore net electric field will be like this, right? So therefore if both my x-axis and y-axis electric fields are like this, therefore my net electric field will be just basically the square root sum of the, let's say, x-axis electric fields and y-axis electric fields. All right, so that's my net electric field. Now you see, if my sigma x and my sigma y are equal, that means I have same charge distribution in the x-axis and y-axis direction. Therefore my ex and ey has to be same, right? So therefore my net electric field will make a 45-degree 45-degree angle with the positive x-axis, right? So therefore, my electric field lines, the net electric field lines will make a 45-degree angle with the positive x-axis. Now, remember that the relations, but you have to find the equipotential surfaces, right? And my equipotential surfaces and the electric fields are basically related by this equation, right? This line integral. So therefore, if I can just manipulate it, I can find that my electric field is just basically nothing but the change of the potential with respect to the distance. And this derivative means, like, for example, this is a derivative. That means my electric field is a derivative of the potential, right? So therefore, if I have a, let's say, potential curve, let's say a sinusoidal, my electric field will be the first derivative, which means at each point it's the gradient, right? So it has to be the gradient. Now you see my gradient line, like if this is my V curve, this would be my E curve, right? The gradient. So you see my E and V are always perpendicular to each other, right? So therefore my equipotential surfaces are always perpendicular to the electric field lines. And since my net electric field lines are 45 degrees with respect to the positive x-axis, my equipotential surfaces would be perpendicular, right, to this surface. So it has to be, right, perpendicular to this surface. So that means with the positive x-axis, what's the angle my equipotential surfaces are making? 135 degrees, right? It's 90 plus 45. So therefore my option D is the correct option. Here we see a voltage curve across an inductor with respect to time, and you have to find out the value of the current through the inductor at time 6 seconds. Now you see at 6 seconds my voltage is going from negative 4 volt to 0 volts, but the current through the inductor cannot change immediately, right? Similarly, the voltage across a capacitor cannot change immediately. So we are going to use this concept to derive out the current through the inductor at t equal to 6 seconds, because the current at t equal to 6 seconds will be basically the current which was just before 6 seconds, because immediately when you turn off the voltage, the current cannot change instantaneously, right? So therefore the current at this region, let's say just before 6, which I can term as t equal to, let's say, 6 minus, which means just before 6 seconds, will be the same current as t equal to 6 seconds, right? Now, remember, for the voltage and current relationship for an inductor is L di dt, right? So therefore, my current will be just 1 by L integral of the voltage across the inductor, right? So now the voltage across the inductor, now for this one we have one voltage, we'll have one current, but you see for the next 2 seconds there is 0 volts. So therefore basically this current which was because of the voltage which was supplied for 2 seconds will be uh, dissipated through the inductor when for the next 2 seconds, right? Because for these 2 seconds the voltage was supplied, so therefore the next 2 seconds when the voltage was not supplied, the energy stored for this region will be dissipated for the next 2 seconds. All right, it will be dissipated here. So we don't have to take into account for the voltage of the first portion. Now we have to just take into account for the voltage of the second portion, which is for 4 to 6 seconds, right? This portion is important to us. Now remember, this is an integral of voltage, right? Voltage of time axis. So now we have a voltage with respect to time. So therefore the integral means basically the area under this curve, right? So therefore I can write the area. So basically I can write 1 by L. So in this case my L is 2 Henries, right? And the integral of V with respect to T is basically the area under the curve, which is basically a rectangle, right? Which is just a rectangle. Now, what's the area of the rectangle? It's 2 times the time, which is 2 seconds, times minus 4, right? Which is the voltage. So therefore, the area under the curve, the integral is just basically 2 times minus 4, right? So therefore, my current is just minus 4 amperes, right? So therefore, my option would be, the correct option would be option B. Okay, in this case, we see that there is a current IT that is being supplied to this solenoid, which is a larger coil diameter. And inside that larger coil diameter, another small coil is placed with a smaller diameter. The dimensions and the number of turns are given in the table that you can see. Now you have to find out the amount of the magnitude of the electromotive force or the induced EMF in the smaller coil because of the magnetic field generated by the current IT that's flowing in the solenoid. Now, if there is a current IT flowing through the solenoid, right? Like for example, if I have a solenoid like this, now if I have a current flowing, right? So because of the current flowing, I will have a magnetic field through the solenoid, right? So in this case, I will have, let's say, for example, in this case, if I assume the current is flowing in this direction, therefore I will have, and if I assume that the rotation of the coil, so therefore my magnetic field will be just fixed to the solenoid, right? It will be going like this, but inside the solenoid, which is of our interest, it's fixed, right? Because we have to find out the magnetic field inside the solenoid where the coil is placed. So now for a solenoid, the magnetic field is found by this equation, right? In this case, your I is a function of time, so I'll just write mu naught NIT. Now your N is basically 10,000 in this case, and we have saw mu naught is the constant. So if you plug in the values, you'll end up having this much IT, right? This much Tesla flowing inside the solenoid. Now, inside the solenoid, you have a constant magnetic field of this B, right? Now, inside that constant magnetic field, you have, let's say, another coil. Now, for sure, this will induce EMF across the coil, right? Because your IT is a function of time, so therefore your B magnetic field is also a function of time, which is changing with respect to time. And if you have a time varying magnetic field, it will induce a EMF across the smaller coil, which you have to find. Now remember, for the induced EMF, the equation is from the Faraday's law. It's given by minus n, which is the number of turn of the loops, multiplied by d phi b, which is the flux changing with respect to time. Now, what's my flux? Flux is basically phi b is just basically b times area, right? And we know the b, but what's my area? Area is the circular area of the smaller coil, right? The diameter, the circular area of this smaller coil, right? This one. this one. Area of the coil is basically pi times r square, right? In this case, it's the r given, it's the diameter given in millimeters, so you have to convert that into meter. So that has to be 0.002 divided by 2 squared, right? So that's the diameter by 2 is the radius squared in meters. Now, if you plug that in, you'll find your phi b moving through the coil to be also a function of time, because we don't know IT. So this is gonna be 0.0395 IT microweber. That's like 10 power minus 16. Now, once you plug these phi b into the Faraday's equation, the N in this case will be 5,000, because we are looking for the induced EMF in the smaller coil. So therefore, once you plug the values in, you'll get like 5,000 times 0.0395, 10 power minus 6 IT, right? So once you plug these values in, you'll get 0.197 millivolts. This will also be a function of time. So basically, this will be 0.197 IT millivolts. All right. Now here we see an electrical circuit. So the point to understand here is that in this region, you have zero current flowing, 0 ampere flowing. So basically, the circuit on the left is disconnected from the circuit on the right, but they are connected via the dependent source. All right, the dependent current source in this case. Now you have to find out the Thevenin equivalent circuit A between the terminals A and B. So the left-hand portion of the circuit, this of the circuit, you have to find out the Thevenin equivalent for this circuit. Now you see that if I consider the Thevenin equivalent of the circuit, so I have to find out basically the equivalent circuit of across, so basically this equivalent circuit across the terminals A and B. Now for my Thevenin, I need, so for the left hand portion, I just need, I have to represent this by something like a voltage source and a resistance, right? So I have to find out this equivalent. Now you see in this case, I have to find out this voltage, right? This voltage, which is my VThevenin. I can term this as VThevenin 1, right? So I'll just write here VThevenin 1 or Thevenin 1. So you see what's my current I naught? My current I naught is just basically my I naught is 10 volts by 2 kilo ohms, right? So that's basically equivalent to 5 milliamperes. So now if my I naught is 5 milliamperes, I have how much current flowing in this circuit? It's 10 I naught, right? 10 I naught, so which is basically equivalent to 0.05 ampere. So what's the voltage I get across the 5 kilo ohms will be the same as my VThevenin 1. In this case, if the current is, since the current is going from the bottom direction, the polarity, the actual polarity will be like this. So therefore my VThevenin 1 comes out to be negative 5,000 into 0.05, which is basically equal to minus 250 volts. All right. Now, this is my VThevenin 1, and to consider RThevenin 1, I have to turn off all the independent sources from the left-hand side circuit. In this case, the only independent source is the voltage. And if I turn off the voltage source, it's short circuit, right? And if I turn off the independent current source, it's open circuit. And since there's a dependent source, I have to consider plugging in a voltage or current source to find out the RThevenin. So let me turn off my voltage source. So this will be a short circuit. So now if this is a short circuit, you see what's my I naught? My I naught is 0 ampere, right? If my I naught is 0 ampere, I will have what's gonna be my this source, which is 10 I naught, is gonna be 0 ampere, right? So if this is 0 ampere, the dependent source will be considered turned off. So if this dependent source is considered turned off, I will not have a dependent source here. So basically this dependent source is out of the circuit. So you see, I just have only this 5 kilo ohms across my terminals, right? So therefore my RThevenin 1 in this case is just 5 kilo ohms. So my actual Thevenin circuit will be basically, I consider it to be like this, right? But it's gonna be, since my Thevenin voltage is negative, so I can also consider something like opposite polarity, right? I can consider like this. So this is my 5K, right? And I can consider opposite polarity with the voltage of 250 volts. Okay, so that's my part A. So for the part B, you are required to find out. So this is for my part A, and for part B, you are required to find out the Thevenin equivalent of circuit B. So that is for the right hand circuit. Now forget about the left hand circuit, right? So I can write my left hand circuit to be, let me just draw it here, 250 volts. I can write this RThevenin upwards or downwards, doesn't matter because it's in series. So I'm supposed to have this to be my RL, right? Okay, now I have to find out the circuit B equivalent, right? So if you consider the circuit B, just ignore everything on the left hand side. So you have to find out the voltage of this one, right? So this I can term as VThevenin 2, right? Now, if you see that if I keep the RL open, right? So there will be no current through this 2 kilo ohms, and there will be no current through this 3 kilo ohms, right? Because the current will be 0. So therefore the voltage drop across these 2 kilo ohms and this 3 kilo ohms is also 0. So therefore my VThevenin will be just basically equal to the voltage drop across these 2 kilo ohms. Right, so basically I have what, a series circuit, 10 volts in series with 3 kilo ohms, 2 kilo ohms, and 5 kilo ohms, right? So I can just apply, and in this case, you see the current is flowing also to the positive direction. So the polarity in this case would be the same as the polarity that I get for the VThevenin also. So I can just apply a voltage divider in this case. So therefore my VThevenin 2 is just gonna be 2 kilo ohms divided by 2 kilo ohms plus 3 kilo ohms, all the series resistances, right? 5 kilo ohms times the 10 volts. So therefore, in this case, my VThevenin should be 2 volts. And what's my RThevenin 2? So also in this case, I have to turn off all the independent sources. So in this case, I have a voltage source. So I turn off the voltage source, it will become a short circuit. So you see I have, in this case, I have something like this, right? I have 2K, 3K, 2K. So this is my 3K, and this is the 5 kilo ohms. So you see I have 3 kilo ohms in series with 5 kilo ohms, parallel with 2 kilo ohms. This one is in series with 2 kilo ohms and 3 kilo ohms, right? Therefore, if I find out the combination of the resistances, I'll get my RThevenin to be 6.6 kilo ohms, right? So therefore, my Thevenin equivalent circuit would be 6.6 kilo ohms, right? And since I consider the voltage polarity to be upwards and it's also positive volts, I can consider this to be 2 volts like this. Okay, so you can ignore this this connection. So therefore, this is for the circuit B, this is for the circuit A, right, across the load resistance RL. Now, for the third part, you're required to find RL for maximum power transfer, right? So let me redraw the circuit. So basically, you have to find out the value of RL such that you have maximum power transfer through it. Now I'll just connect the two circuits together. And I'll keep the RL, which was supposed to be here, which was supposed to be in this position, right? I just keep it open. Now I have to find out the value of RL such that I have maximum transfer from both the left-hand circuit and the right-hand circuit, right? So basically I have to find another Thevenin across this RL, assuming that RL is open. So I have to find out this VThevenin again, which I can term as VThevenin 3, and the resistance across it, right? So therefore you see, since this is a series circuit, right? You see this is a series circuit, so basically the total source will be just 252 volts, right? In series with 5K and 6K. So if I find out the voltage across the 5 kilo ohms in this case, so I can basically apply KVL across these terminals, right, to find out my V Thevenin, right? 3. So basically my V Thevenin 3 should be equal to minus 250 plus V across the 5K, right? So what's the V across the 5K? So I can just apply the voltage divider, right? So that's like 5K divided by 5K plus 6.6K, the total series resistances, multiplied by 252 volts, because these both polarities are in the same direction, so the current is flowing in the same direction. So I can add the sources up. So I will get a voltage of around 108.6 volts, right? So therefore, if I plug it in this equation, I'll get my VThevenin to be minus 141.4 volts, right? So that's my VThevenin 3. And what's my RThevenin 3? So you see, for that one, I have to short circuit both the independent voltage sources, right? So therefore, what I am looking for is just something like this. Right, so you see, in this case, my RThevenin is just basically 5K parallel with 6.6K. So in this case, my RThevenin would be 2.85 kilo ohms, right? So therefore, my ultimate Thevenin circuit would be, I give negative terminal up, positive terminal down, because my voltage V Thevenin was negative, and I put 141.4 volts. This one is 2.85 kilo ohms. So that's my ultimate Thevenin across the RL. So now what's gonna be my RL for maximum power transfer? My RL has to be equal to the Thevenin resistance, right? So which is has to be equal 2.85 kilo ohms for maximum power transfer, which is basically 50% of the power that is supplied by the Thevenin voltage. Now here we see a transient circuit. So you see basically initially the switch was at position A, and then the switch was moved to position B at time equal to 0 seconds, and then again the switch was moved to position C at time equal to 5 seconds. All right, so now you have to find out the time constant of the circuit when the switch is in position B. So therefore, when the switch is in position B, right? So when the switch is in position B, so the circuit is completed. So you see the capacitor will be charging up, right? Because initially you can assume that the capacitor was zero, because they already also mentioned that it has zero stored energy. That means initially the voltage of the capacitor was 0 volts, right? So now when you turn the switch to position B, it will be charging up, and once it's continuously being charging up, after a certain point when it's fully charged, it will be an open circuit, right? So now you have to find out the time constant, right? So the time constant for position B is basically tau equal to R Thevenin across the capacitor times the capacitance, right? So we know the capacitance is just 10 microfarad. Now we have to find out the R Thevenin across the capacitor. Now what's the R Thevenin across the capacitor? C1, right? We have to consider C1 because they also have asked because for position B, you see only the only capacitor that's charging up is C1. So this R Thevenin has to be across C1, and this is also C1, right? So therefore, what's the R Thevenin across C1? You have to turn off all the independent sources. So you turn off the current source IS. So you have just basically R1 in series with R2 parallel with R3. So that's your R Thevenin, right? So your R Thevenin is just 3K plus 3K in parallel with 6K, right? So this is just 3 kilo ohms. So now what's your time constant? 3000, which is R Thevenin times 10 microfarad, which is basically equal to 0.03 seconds. Okay. Now you have to find out the voltage across VC1 as a time function between 0 seconds to 5 seconds. That means for the when the switch has been moved from position A to B, before you move it to position C. That means for between the time duration 0 to 5 seconds, because at time 5 seconds you're moving the switch to position C. So now if you have to find out the voltage function across the capacitor, you have to use this. You have to use this form of the equation, which is V final, right? Plus V initial minus V final times e power minus t by tau, right? So now since we are considering for time duration 0 to 5, I know my tau already, right? It's 0.03 seconds. Now what's my initial voltage? So now since you already started with a 0 volt, you know the capacitor has to be 0, like it has to be a 0 volt when it started with. Now what's my V final? So basically when the capacitor is fully charged, the capacitor will be open, so therefore there will be no current through the capacitor here. So therefore the voltage across the capacitor C1 will be the same as the voltage across R3, right? So now you can find out the voltage across R3 because your IS is just splitting up into two branches, right? So you can apply the current divider in this case, right? So therefore by current divider, if you apply the current divider, you can find your VF to be R3, right? R3 times the current going through that one, through R3, which is basically 3 kilo ohms divided by 3K plus 9K times 200 milliampere, right? So times 200 milliamps. So once you plug in all the values, you're gonna find your VF to be 300 volts. All right. Now, once you have all the values, what's your VCT? Your VC1T is just basically 300 plus 0 minus 300 e power minus t by 0.03, which is just basically 300 minus 300 e power minus 33.3 t. This much volts, right? Okay. Now you have to find out I1T, right? You have to find out I1T, which is the current through the C1 for t greater than 5 seconds. So now remember at t 5 seconds, your switch has been moved to position C, right? So that's your circuit. So now the entire circuit on the left hand side is disconnected, right? So you just have to consider the circuit on the right hand side. So now remember you have to find for t greater than 5 seconds the I1T. Now we know what was the voltage at 5 seconds for the voltage across the capacitor C1 at 5 seconds, right? So we know the voltage equation for C1, right? So that was like when it was at position B, we know it was 300 minus 300 e power minus 33.3 t, right? So at 5 seconds was the voltage across the capacitor. So when you multiply 5 times this one, so you know this is a very high exponential value, very small exponential value. So basically this will end up giving you 0. So you will have VC1 at 5 seconds just gonna be 300 volts, right? So that's your starting voltage, right? So that's like your V initial, right? In this case, when the switches move to position C, so that's your initial, right? And what's your V final voltage? So after, if you keep it connected, you know that your capacitor will discharge through this resistance, right, to 0 volts. So your V final is just 0 volts, right? Now, if I want to write VC1 T equation for time greater than 5 seconds, it has to be also of a similar form, right? Vi minus Vf e power minus t by tau. So now I know my Vf, which is 0 volts. I know my Vi, which is 300 volts. But what's my tau? Now remember, now the tau is basically R Thevenin C, right? But you see, my R Thevenin is just changed right now, right? My R Thevenin is just basically the series resistance, which is just basically 18 kilo ohms, right? So it changed. And now what's my C? My C is no longer 10 microfarad because now I have two more capacitances in series. So my C is basically the series capacitance of C1, C2, and C3, right? So what's my net capacitances? Since these are in series, so this I can just do the inverse addition, right? Because in series capacitor adds up like the resistances in parallel, right? So this is 10 microfarad, right? So, okay. So this has to be in farads, right? So I don't know why it's given microcoulombs. All right, plus 1 by 3 microfarads, right? Plus 1 by 6 microfarads. So now your net capacitance, right? So you're in this case also you'll get a net capacitance which is different for the 10 microfarad capacitances, right? And R Thevenin, your R Thevenin is 18 kilo ohms, right? So now what's your new tau? So once you plug in the values, R Thevenin times C net, once you plug in the new values, fortunately, you will also find that it's the same value as before, which is 0.03 seconds. Yes. So now you plug in these values to find out your VC1T for time greater than 5 seconds. So in this case, it's 0 plus 300 minus 0 is 300 e power minus 33.3 times. So what's your new voltage is 300 e power minus 33.3 T, right? So that's your new VC1 T for T greater than 5 seconds. Now you have to find I1 T, right? So now we know the voltage and the current relations for the capacitor, which is just basically my IT is C1, my IT is just C dV dt, right? Now, in this case, you know your VC1T, right? You know your VC1T, right? And you find out the current I1T. So why don't you just, in this case, this plug in all the values. So basically, in this case, your I1T is the current through the C1. So you can plug this as C1, and dV is basically dVC1T, right? By dt. So once you plug in all the values, is 10 microfarad times the differentiation of this will be 300 times minus 33.3, right? Exponential minus 33.3 t. So you'll end up having a value of 0.1 e power minus. Okay, so since here the switch was closed at 5 seconds, so this equation will be just t minus 5. This is one thing you have to consider. So you will get minus 0.1 e power minus 33.3 t minus 5. Right, so that's your I1T. All right, so for the last questions, you see that you are asked, so this is an AC circuit, so you are asked to find out the Thevenin equivalent circuit between terminals A and B for omega equal to 200 radian per second. Now you need this omega to calculate the impedance or the reactance of the inductor and the capacitor. So now you have to find out the Thevenin equivalent circuit across A and B. Now I can write these all in the phasor form, right? So basically this will be 10. Now everything is to convert everything in the phasor form, consider everything in the cosine format. So this is already given in cosine format, so I don't have to do anything here. So it's 10 angle minus 90. This one is 5 angle 0, right? Milliamperes. Now, what's my ZL? The impedance, the reactance for 5 Henries, right? So that's just J omega L. So in this case, it's just J times 200 times 5, right? So that's like 1K. What's my ZC? The reactance of the capacitor is 1 by J omega C. So that's like minus J. Once you plug in all the values, you'll find out it's minus J 5K. Right, so I can just write here this one as minus JK, and this one I can write J1K. Right, so I can just ignore this 5 Henry and just ignore this 1 microfarad. So this is my phasor domain diagrams, right? So I can also ignore these time domain things, right? Okay, so that's my equivalent circuit. Now I have to find out the Thevenin equivalent, right? So for the Thevenin equivalent, what I need is I have to compute the Thevenin voltage across this terminal, right? And the Thevenin impedance in this case. All right, now to find out the Thevenin voltage, what I could do is, okay, so let me just do the Thevenin impedance right now. So basically my Thevenin impedance will be, I turn off all the independent sources, so my voltage source will be short, right? And my current source will be open, so I will just have basically this 1jk, right? So I'll have something like this. J1k. This is my capacitor, right? So I can also consider this as to be an impedance, so it's minus 5jk, 2k. So that's gonna be my Z Thevenin, right? So my basically Z Thevenin is gonna be just one this inductor reactance, right? In parallel with this capacitor reactance, right? Parallel with 2 kilo ohms. All right. So once you plug in all the values, you will find out that your Z Thevenin is this much, right? So now you have to find out the V Thevenin, right? So now for V Thevenin, what I could do is like, so you see I'm considering this circuit, so I can apply mesh or nodal, but in this case I just can use nodal to simplify, because you see if I consider this to be one node, then basically I just have to compute for one node. So if I write this as V1, so my V Thevenin will be just the nodal voltage V1, right? So if I apply nodal analysis considering current going out from all the nodes, right? So I have to consider 4 currents in this case. So what's gonna be my nodal equation? It's gonna be V1 minus 10 angle minus 90 divided by J1K, right? That's the leftmost current, plus, in this case, I'm considering current going downwards, but current source is pushing current up, so it's gonna be minus 5 milliamperes, right? And then it's plus V1 by minus 5 JK, that's the current through the capacitor, plus 5 V1 by 2K, right? That has to be equal to 0. So you see in this equation, I just have V1 as my variables, right? So when I solve this equation, I will get my V1 to be 5.3 angle 122 degrees. This much volts, right? So this is same as my V Thevenin. All right. So now my Thevenin equivalent circuit is 5.3 angle. Now this is minus 122, so it's minus 122. This one is 1060 angle 60. So that's my Thevenin equivalent. All right. Now, for the second part, you are asked to find out the ZL for maximum power transfer. You have to find out what's the ZL, right? Now remember, for resistances, it was always R Thevenin equal to RL, and those are real values. But here you have an imaginary part, the reactances, right? So for this case, your ZL has to be Z Thevenin conjugate, right? So what that means is basically your ZL will have the same magnitude as the Z Thevenin, but an opposite angle. In this case, if the angle was plus 60, my angle will be minus 60. If the angle of the Z Thevenin was minus 60, my ZL has to be plus 60. So basically the angle would change, or the imaginary part would change. For example, if my Z Thevenin, let's say if my Z Thevenin was something like A plus JB, my ZL has to be A minus JB. All right. Or if it was A minus JB, my ZL has to be A plus JB. The imaginary part would reverse the sign.